Hi students, in the last video we looked at some special discrete distributions. In this video we look at some more discrete distributions, then we'll start to look at some special continuous distributions. Okay. Here is another discrete distribution, something called hypergeometric distribution. Suppose a population consists of capital N items in which capital M are type 1, remaining capital N minus M are type 2. And small n items are drawn at random from the population without replacement. In this experiment, let x denote the number of type 1 items in the selection. Here we cannot say x follows binomial distribution, though we are kind of performing sequence of n Bernoulli trials, because getting type 1 item we can see as a success, type 2 as a failure. So selecting this n items is like a performing n Bernoulli trials, but these Bernoulli trials neither independent nor identically distributed, because these n items are drawn without replacement. If we had drawn with replacement, then these n trials would have been independent and identically distributed. Then we would have said x follows binomial distribution with a parameter n and the probability of success p capital M by capital N. But that is not the case here. These n items are drawn without replacement. That's why x is not going to follow binomial distribution. Okay. First let us see the support of x. Here x can take the value between maximum of 0 comma n minus of capital N minus capital M and the minimum of capital M comma small m. Simple here, if the sample size is bigger than number of type 2 items, then you cannot have a 0 type 1 items in the selection. You should have at least n minus of capital N minus capital M type 1 items, because you cannot get all type 2 items because your sample size is bigger than number of type 2 items. Okay, you should have at least n minus of capital N minus capital M type 1 items. That's why x will be at least this much when small n is bigger than capital N minus capital M, otherwise it's going to be 0. Fine. And also x cannot be more than minimum of capital M comma n, because x cannot be more than number of type 1 items, which is m. Okay, x also cannot be more than the sample size, number of items we are selecting. Okay, so this is the support. Now let's look at the PMF function. The Px of x is probability of x equal to x, which is going to be capital M choose x times capital N minus capital M choose n minus x divided by capital N choose n. Here outcomes are like a n combinations of capital N items. So the sample space size is going to be capital N choose n, and the number of outcomes that are favorable to the event x equal to x is capital M choose x times capital N minus capital M choose n minus x. So this is the PMF function. Fine. Now let us check the validity of this PMF. First of all, we can easily see that the PMF values are positive or the support. Now let us sum up the PMF values or the support. Okay, sum of the PMF values or the support. This is the PMF at x. Now we have a common denominator n choose n. Now the numerator add up to n choose n by Vandermon's identity, because by Vandermon's identity numerator we can write m plus capital N minus m choose small n. Okay, because I think I stated Vandermon's identity like this: m plus n choose r equal to summation k equal to 0 to r m choose k n choose r minus k. Here capital M is like a small m, and capital N minus capital M is like a small n, and small n is like a r. Okay, so here x is like a k. Okay, so this is a Vandermon's identity. So we can see this one equal to this. Here mm cancel, it's going to be n choose n. Okay, So by Vandermon's identity, numerator actually going to be equal to capital N chosen. So that's why the PMF values add up to 1. Okay. Here X is said to have something called hypergeometric distribution with the parameter capital N, which is the population size, and capital M, which is the type 1 item size, small n, which is sample size. Okay. Here is the notation. We read it as X follows hypergeometric distribution with the parameter capital N, capital M, small n. Okay. And from assignment 3, we know that for this distribution, expectation of X is n capital M by capital N, and the variance of X equal to n capital M times capital N minus capital M times capital N minus small n by capital N square times capital N minus 1. This is the variance of X. Okay, and we are not going to look at MGF. It's not going to be in simple form, and we won't use it much. Okay, let's not worry about it. Now let me show you interesting application of these results. Something called capture recapture method. Okay, let's say we want to estimate fish population in lake. Okay, let capital N total fish in the lake, that is unknown, that we want to estimate. What we do, first we capture capital M fish from the lake and mark them and release back to the lake. Next day again we catch small n fish at a random locations of lake. Say we got small k marked fish in the catch. Okay, here capital N is total fish, that is unknown, and capital M is number of marked fish, small n is size of the second catch, and small k is number of marked fish from the second catch. Okay, here there are two types of fish in the lake now. Type 1 marked fish, type 2 unmarked fish. Okay, so let X denote the number of type 1 fish from the second catch. Okay, so then X follows hypergeometric distribution with a parameter capital N, capital M, small n. Okay, here small k, which is the number of marked fish that we got from second catch, should be approximately equal to expected number of marked fish from the second catch. That is, expectation of X should be approximately k. And we know that for hypergeometric distribution, expectation of X equal to n capital M by capital N. Therefore, n capital M by capital N should be approximately equal to k. That implies capital N should be approximately equal to capital M n by k, since expectation of X equal to n capital M by n. Therefore, approximately lake will have capital M n by k fish. So this is how you can estimate number of fish in the lake. This is a widely used technique in practice. Okay? Okay, fine. Poisson process. We consider an event occurrences over a time, distance, area or volume happening under a Poisson process, provided they satisfy the following conditions. Before I state those conditions, let me explain those conditions with an example. Okay, let us consider email occurrences over a time in a day. Email occurrences over a time in a day satisfies following three conditions. Condition 1, the probability of single email occurrence during the small time interval is proportional to the length of the time interval. That is, bigger the duration, bigger the chance, lesser the duration, lesser the chance. Also, this probability should not depend on the location of the time interval. That means it should not be matter whether it is a morning or afternoon or evening. It should be dependent only on the length of the time interval. Okay. Condition 2, the probability of more than one email occurrence during the small time interval is negligible. That is, see, a typical person may not even get 10 emails in a day. If I ask you, what is the probability you get more than one email in 1 minute time period? It's very, very small, so it should be negligible. Okay? And condition 3, number of email occurrences during the disjoint time intervals are independent. That is, Number of emails you get from morning 9 to 10 should be independent of number of emails you get from 10 to 11, 11 to 12 and so on. Okay. So here email occurrences over a time in a day satisfies these three conditions. So let me state these conditions for general event of occurrences over a time. Similarly, you can mention for a distance, area, or volume. Okay. So condition 1, the probability of single event occurrence during a small time interval is proportional to the length of time interval. Condition 2, the probability of more than one event occurrence during a small time interval is negligible. Condition 3, the number of event occurrences during disjoint time intervals are independent. Okay, so we say event occurrences over a time happening under a Poisson process provided they satisfy these three conditions. Let's look at some examples. Okay, examples. Example 1, email occurrences on a given day over a time. Already explained why it satisfies three conditions. Example 2, wrong telephone numbers that are dialed in a day over a time. Feel free to verify three conditions for this example. Okay. Example 3, misprints on a page of a book over area. Let me explain three conditions with this example. Okay. The probability of single misprint over a small page proportional to the area of the page. Bigger the page, bigger the chance, smaller the page, smaller the chance. And also this probability should not depend on the location of the page. Doesn't matter which page number it is, so the probability should be same. It should be depending only on the page area. Condition 2, the probability of more than one misprint in a small page should be negligible, because in whole book you hardly find 3-4 mistakes. What is the probability you find more than one mistake in a small page? It should be negligible. Okay. And condition 3, the number of misprints over different pages must be independent, right? Okay. So that's why these misprints over area happening under Poisson process. Fine. Okay. Example 4, people living more than 100 years in a community or area. Feel free to check three conditions. Okay. Example 5, packages of dog biscuits sold in a particular store over a time. You can also verify three conditions for this example. So they are happening under a Poisson process over a time. Example 6, customers entering in a post office, bank or shopping mall on a given day over a time. You can also verify three conditions for example 6. Okay, so these are the event occurrences happening under a Poisson process. Okay, now Poisson distribution. Consider a Poisson process over a time. Similarly, you can consider a Poisson process over a distance, area or volume. Let me consider a Poisson process over a time. Let x denote the number of event occurrences in unit time interval 0, 1. Here x can take the values 0, 1, 2, 3, so on, because we may have any number of event occurrences in the interval 0, 1. That's why the support of x is going to be 0, 1, 2, 3, so on. Fine. Now, what we do, let us divide the interval 0, 1 into n non-overlapping subintervals of equal length, okay, for large n, okay. So, here the ith subinterval going to be interval I minus 1 by n to I by n. The length of the ith interval going to be 1 by n for all I equal to 1 to n. As you can see, each subinterval having equal length 1 by n. Here n is large, so length of each subinterval is very, very small. Fine. Now here these event occurrences happening under Poisson process. So during any subinterval II, we can expect at most one event occurrence, because By condition 2, the probability of more than one event occurrence during the small time interval is negligible. That's why we cannot expect more than one event occurrence during any time interval IA. Okay, fine. Now, to observe number of event occurrences over the interval 0, 1, we can do the following thing. First start with the count 0. See if there is occurrence during the I1. If yes, increment count by 1. Then see if there is occurrence during the interval I2. If yes, increment count by 1 and so on. See if there is occurrence during the time interval In. If yes, increment count by 1. This is how we can observe total number of occurrences in the interval 0, 1. Now, here we kind of performing sequence of n Bernoulli trials, right? Because each time we are asking if there is occurrence or not. If there is occurrence, we may see as a success, otherwise failure, right? So we kind of performing sequence of n Bernoulli trials. And if the probability of success for each Bernoulli trial going to be same, because the probability of success is what? The probability of single occurrence during the time interval II, and this should be proportional to the length of the subinterval by condition 1. Okay, and let us say lambda is the proportional constant, and we know that each subinterval having same length, which is 1 by n. That's why the probability of success is going to be same, lambda by n, for each trial. That means we are kind of performing sequence of n identical Bernoulli trials. Fine. And by condition 3, we also know that number of event occurrences during the disjoint time intervals are independent. That's why these trials also should be independent. So, to observe number of event occurrences in the interval 0, 1, we kind of performing sequence of n independent identical Bernoulli trials, each with a probability of success lambda by n. That's why this x must follow binomial distribution with a parameter n comma lambda by n. Okay, fine. Now, so x follows binomial distribution with a parameter n comma lambda by n. So the PMF function Tx of k, which is probability of x equal to k, using binomial PMF we can write n choose k lambda by n to the power of k 1 minus lambda by n to the power of n minus k. Okay. Now from lecture 16 we know that as n go to infinity, this binomial PMF approaches e power minus lambda, lambda power k by k factorial. Okay, this we have seen in the lecture 16. So therefore, the PMF Px of k equal to e power minus lambda, lambda power k by k factorial for k equal to 0, 1, 2, 3, so on. Okay, let us check the validity of this PMF. First of all, PMF values are positive over the support k equal to 0, 1, 2, 3, so on. And let us sum up the PMF values over the support. Summation k equal to 0 to infinity e power minus lambda, lambda power k by k factorial. If you write this e power minus lambda out, e power minus lambda summation k equal to 0 to infinity lambda power k by k factorial. We should know the expansion of e power x, that is summation k equal to 0 to infinity x to the power of k by k factorial. So in place of x we have a lambda here, so this must be equal to e power lambda. So e power minus lambda times e power lambda equal to 1. Okay, so the total PMF values or the support equal to 1. So the two conditions are satisfied. So what we got is actually valid probability mass function. Okay, here x is said to have Poisson distribution with the rate parameter lambda. Lambda is a proportional constant. Okay, fine. We have a notation here. This is a notation. We read it as x follows Poisson distribution with the parameter lambda. We already worked out mean and variance for this distribution in previous classes. We know that expectation x, variance of x both are equal to rate parameter lambda. Okay. Now let us see what is the MGF. MGF mx of t, which is the expectation of e power tx. So it's going to be what? Summation k equal to 0 to infinity e power tk px of k. What is the PMF here? E power minus lambda, lambda power k by k factorial. If you write this e power minus lambda out, let's group e power tk lambda to the power of k like this. Lambda e power t over to the power of k. Now, again this look like summation x to the power of k by k factorial for k equal to 0 to infinity, and we know this equal to e power x, right? So this whole thing we can write e power lambda e power t, because in place of x we have a lambda e power t. That's why we have e power minus lambda times e power lambda e power t. So this is going to be equal to e power lambda of e power t minus 1. Okay, so this makes sense for any t between minus infinity to infinity. So this is the PMF. Okay, therefore MGF of the Poisson distribution with the parameter lambda is what? E power lambda of e power t minus 1, which makes sense for any t from minus infinity to infinity. Okay, fine. Note, here the rate parameter lambda actually equal to average number of event occurrences in unit time interval. The reason is this. We just realized that lambda equal to expectation of x for Poisson distribution. And what is x? Number of event occurrences in unit time interval, right? That's why expectation of x should represent average number of event occurrences in unit time interval. That's why the rate parameter lambda actually equal to average number of event occurrences in unit time interval. Fine. Next. Here is an exercise. If x follows Poisson distribution with the parameter lambda, then show that expectation of x, variance of x both are equal to lambda through MGF. We know how to compute mean and variance through MGF, right? So just do this. Fine. Example, customers arrive in a shopping mall at a rate 5 per minute. What is the probability that no customer arrive in 1 minute period? Okay, let x denote the number of customers arrive at a shopping mall in 1 minute. Here we can verify that these customer arrivals happening under Poisson process with the rate parameter lambda equal to 5. Okay, if we think that this 1 minute is our unit time, okay, then we can say that this x follows Poisson distribution with a parameter lambda equal to 5. So its PMF going to be px of k e power minus 5 power k by k factorial for k equal to 0, 1, 2, 3, so on. Here we want the probability that no customer arrive in 1 minute period. That means we are interested in probability of x equal to 0. Okay, so the probability of no customer in 1 minute period equal to probability of x equal 0, which is e power minus 5 power 0 by 0 factorial, that is e power minus 5. So the answer is 0.0067379. This is the probability. Okay, next problem. In a length manuscript, it is discovered that only 13.5% of pages contain no typing errors. Find the percentage of pages that contain one error. Okay, let x denote the number of typing error in a page. We can verify that these typing errors happening under a Poisson process with some rate parameter lambda. Okay, we need to figure out the lambda. First of all, let's say that our one page is our unit area. Okay, then we can say that x follows some Poisson distribution with a parameter lambda. So we need to figure out this lambda first. What is given here? We are given the probability of x equal 0, kind of, probability of x equal 0, 13.5% means 0.135, which is given. From that, we should be able to get the lambda value. Then we are actually interested in percentage of pages that contain one error. That means we are interested in probability of x equal to 1. Now, what is given here? Probability of x equal 0, which is a 0.135. That means probability of x equal 0 means e power minus lambda power 0 by 0 factorial using the PMF of Poisson distribution. That implies e power minus lambda is 0.135. From that, lambda is going to be this log base c 1 by 0.135, which will be approximately 2. That means the rate parameter lambda is approximately 2. Okay, now that implies now the PMF is going to be what? E power minus 2, 2 power k by k factorial for k equal to 0, 1, 2, so on. Now we are actually interested in probability of x equal to 1. Okay. Here we are actually interested in probability of x equal to 1. Now the probability of x equal to 1 going to be e power minus 2, 2 power 1 by 1 factorial, which is 0.2706. Okay. Hence, 27 percentage of pages contains exactly one error. Fine. Okay. Next problem. Each of 500 soldiers in an army company independently has certain disease with probability 1 by 1000. This disease will show up in a blood test. And to facilitate matters, blood samples from all 500 are pooled and tested. What is approximate probability that blood test will be positive? See here, the blood test will be positive if at least one of them has a disease, because all blood samples are pooled and tested. So the blood test will be positive if at least one of the soldiers have a disease, right? Fine. Here, each person may have a disease or not. If person has a disease, let's call it success, otherwise failure. Okay. The probability of success, that is probability of person have a disease, is 1 by 1000, which is given. That is 0.001. So P is going to be what? 0.001. Now, testing for the disease of these 500 soldiers is like a performing sequence of 500 independent identical Bernoulli trials, each with a probability of success 0.01. Then, if I let x equal to number of soldiers who has a disease among 500 soldiers, that is x is number of success in 500 Bernoulli trials, then x follows binomial distribution with a parameter 500 comma 0.001. Okay. Now here blood test will be positive if and only if x greater than or equal to 1. Blood test will be positive if and only if at least one soldier has a disease, right? That means x must be greater than or equal to 1. That is, we are interested in probability of x greater than or equal to 1. So probability of x greater than or equal to 1 is 1 minus probability of x less than 1. X less than 1 means x must be equal to 0, because x can take only 0, 1, 2, 3, so on. So this is nothing but 1 minus probability of x equal 0. Now for probability of x equal 0, let us use binomial PMF, which is 1 minus the probability of x equal 0 I am writing as 500 choose 0, 0.001 to the power of 0, 1 minus 0.001 to the power of 500, because here p equal to 0.001 and n equal to 500. Okay, so fine. So now, so 500 choose 0, 1, something to the power of 0, 1. So this is going to be 1 minus 0.999 to the power of 500. Okay. So this will be simplified to 0.393621 and so on. But this needs lots of computation. Okay. To compute 0.999 to the power of 500, we have to use lot of computational power. Okay. So it's not cheap, it's expensive computation. Actually, in this case, we can do better. We don't have to do this much computation to get the approximate probability, because here n is 500, which is large, and p is 0.001 small, and np is of moderate size of, which is going to be our lambda. So in this case we can use Poisson approximation to binomial distribution. Okay, let's see that. Here n is large, p is small, np is of moderate size, which is going to be our lambda. So we can use Poisson approximation to binomial distribution. That is, this binomial PMF will be approximately equal to e power minus lambda, lambda power k by k factorial when n is large, right? Now, probability of x greater than or equal to 1, which is 1 minus probability of x equal to 0. This time, we can use Poisson approximation for probability of x equal to 0. So, we can write probability of x equal to 0 as e power minus 1 by 2, 1 by 2 to the power of 0 by 0 factorial. That is, this gets simplified to 1 minus e power minus 1 by 2, that is 1 minus 1 by root g. So whose value will be this 0.39346934 Okay. Now this will be pretty close to the previous answer that we obtained using binomial distribution. But the good thing is here we didn't use much computation like we did earlier. Okay. So that's why whenever we have a large n small p with a np moderate size, your lambda should not be too large again. Okay, then it's a very good idea to use Poisson approximation to binomial distribution. Okay, fine. Now we are going to look at some special continuous distributions. First, continuous uniform distribution. We can simply call it uniform distribution. Consider the random experiment of selecting a number at random from the interval AB. So in this experiment, our sample space omega is going to be interval AB only. Let us take the random variable x, which denote the number that we are selecting. So the capital X is going to be function from sample space capital omega to R with a mapping omega mapping to omega only. So the support of x is going to be interval AB only. First of all, here let us observe one thing. For a less than or equal to a1 less than b1 less than or equal to b, the probability of we pick a number from interval a1 b1 should be proportional to the length of the interval. It should not depend on the location of the interval. It should depend only on the length of the interval as we pick number at random. Okay, so that means the probability of a1 less than or equal to x less than or equal to b1 should be like k times b1 minus a1, where k is some proportional constant, b1 minus a1 is length of the interval. And we should also have the probability of a less than or equal to x less than or equal to b1, because we always pick number from interval AB. It should be a sure event. That means k times b minus a must be equal to 1. That implies k equal to 1 by b minus a. Therefore, for a less than or equal to a1 less than b1 less than or equal to b, the probability of a1 less than or equal to x less than or equal to b1, that is probability of selecting a number from interval a1 b1, should be equal to b1 minus a1 by b minus a. Okay, with this knowledge we can actually write down CDF of the random variable x. Let's do that. For x less than a, the probability of x less than or equal to x going to be 0, as we never pick number smaller than a. That's why CDF value at x going to be 0 for x less than a. For a less than or equal to x less than b, this event x less than or equal to x, we can actually express union of two mutually exclusive events like this. Okay, so by finite additivity The probability of x less than or equal to x going to be sum of these two probabilities, and this probability going to be 0 as we never pick number smaller than a, and this probability going to be x minus a by b minus a. So the CDF value at x going to be x minus a by b minus a for a less than or equal to x less than b. For x greater than or equal to b, this time this event x less than or equal to x, we can actually express union of three mutually exclusive events like this. Okay, again by finite additivity, the probability of x less than or equal to x going to be sum of these three probabilities, and these two probabilities going to be 0 as we never pick number outside interval AB, and this probability going to be 1 as we always pick number inside interval AB. Okay, that's why the CDF value at x going to be 1 for x greater than or equal to b. Now we can write down CDF capital F of x equal to 0 for x less than a, x minus a by b minus a for a less than or equal to x less than b, 1 for x greater than or equal to b. This is the graph of the CDF. And if you differentiate CDF, you will end up with a PDF, right? So if you differentiate CDF over interval AB, CDF is x minus a by b minus a, whose derivative going to be 1 by b minus a. Okay, so the PDF f of x equal to 1 by b minus a for a less than or equal to x less than or equal to b. Outside interval AB, CDF is constant, so its derivative must be 0. That's why outside the PDF value going to be 0. So we have a PDF which is constant over interval AB outside 0. Since we have a constant density, capital X is just likely to be near any value of the interval AB as any other value. Okay, because f of x actually measures likelihood of capital X being near x. It should be same for all x as we pick numbers at random. Okay, that's why we end up with constant density function here. Fine. Here x is said to have uniform distribution over the interval AB. Here a and b are parameters of the distribution. Fine. We have a notation here. This is the notation. We read it as x follows uniform distribution over the interval AB. And from assignment 3, we know that for this distribution, expectation of x is a plus b by 2, variance of x is b minus a whole square by 12, and we have also seen MGF. Mx of t is e power tb minus e power ta by t times b minus a for t non-zero, and for t equal 0, MGF value 1. So this is the MGF. Fine. Now let's look at the next. Buses arrive at a specified stop at a 15-minute interval starting at 7 a.m. That is, they arrive at 7, 7:15, 7:30, 7:45 and so on. You get the idea. If a passenger arrives at a stop at a time that is uniformly distributed between 7 and 7:30, then find the probability that he waits A less than 5 minutes for bus, B more than 10 minutes for bus. Here we have to answer these two questions. Let x denote the time in minutes past 7 that passenger arrive at the stop. So here x take any value in the interval 0 to 30 as passenger arrives between 7 and 7:30. So here x follows uniform distribution over the interval 0 to 30. So here a equal to 0, b equal to 30. So immediately we can write down PDF and CDF for uniform distribution over the interval 0 to 30 like this. This is going to be PDF. This is going to be CDF. Now let us try to answer A and B. Let capital A denote the event that passenger will have to wait less than 5 minutes for bus. This happens only when passenger arrives between 7:10 to 7:15 or 7:25 to 7:30. If passenger arrives between 7:10 to 7:15, then he will have to wait less than 5 minutes to catch 7:15 bus. If passenger arrives between 7:25 to 7:30, then he will have to wait less than 5 minutes to catch 7:30 bus. Okay? So A happens if and only if x between 10 to 15 or 25 to 30. Therefore, probability of A going to be probability of 10 less than x less than 15 plus probability of 25 less than x less than 30. Okay. Now we can use the PDF of uniform distribution to compute these probabilities. So we can integrate the PDF from 10 to 15 to get this probability. We can integrate the PDF from 25 to 30 to get this probability. So the integral of this is going to be 15 minus 10 by 30, and the integral of this is going to be 30 minus 25 by 30. The whole thing gets simplified to 1 by 3. Therefore, the probability of the passenger will have to wait less than 5 minutes is 1 by 3. Okay. Now, let's answer B. Let capital B be the event that passenger will have to wait more than 10 minutes for bus. This happens when passenger arrives between 7 to 7:05 or 7:15 to 7:20. If passenger arrives between 7 to 7:05, then he will have to wait more than 10 minutes to catch 7:15 bus. If passenger arrives between 7:15 to 7:20, then he will have to wait more than 10 minutes to catch 7:30 bus. That's why this B happens if and only if x between 0 and 5 or x between 15 to 20. Okay. So the probability of B going to be probability of 0 less than x less than 5 plus probability of 15 less than x less than 20. Okay. Now, in terms of CDF also we can answer these probabilities. This is going to be fx of 5 minus fx of 0, and this is going to be fx of 20 minus fx of 15, because we know that probability of a less than x less than b going to be f of b minus f of a, right? Okay. Here continuous distribution, don't worry about whether endpoints are included, all will be equal to f of b minus f of a. So in terms of CDF we can answer these things. So f of 5 going to be 5 by 30 minus f of 0, 0 by 30, and f of 20 going to be 20 by 30, and f of 15 going to be 15 by 30. The whole thing gets simplified to again 1 by 3. So the probability that passenger will have to wait more than 10 minutes for a bus again going to be 1 by 3. Fine. Next. Erlang distribution. Consider a Poisson process with rate parameter lambda. What is lambda here? Average number of event occurrences in unit time interval. Lambda is average number of event occurrences in unit time interval 0, 1. Let xt denote the number of event occurrences in the interval 0 to t. Then what would be the average number of event occurrences in the interval 0 to t? That would be lambda t. So there will be lambda t average number of event occurrences in the interval 0 to t. For a moment, if you think that this is our unit time interval, then this xt follows Poisson distribution with a parameter lambda t. Then the PMF of xt is going to be this. Probability of xt equal to k is e power minus lambda t. Lambda t to the power of k by k factorial for k equal to 0, 1, 2, 3, so on. Fine? Okay. Now, let capital TR denote the time taken for the rth occurrence in the Poisson process. That is, capital TR is what? Waiting time for rth occurrence. Now let us try to find out probability distribution of this capital TR. First, let us look at the CDF. So CDF, capital F of t, is probability of TR less than or equal to t by definition. Now, obviously for t less than 0, this probability is going to be 0 because TR is a positive random variable. It only takes positive values as it is a time taken for rth occurrence. So waiting time, right? Fine. So that's why the CDF value is going to be 0 for t less than 0. For t positive, okay, so what is the CDF value at t? Probability of TR less than or equal to t. That means we can write 1 minus probability of TR bigger than T, okay, because probability of E is 1 minus probability of E complement. Now, TR bigger than T means time taken to have rth occurrence is more than T. That means in the interval 0 to T, we don't have rth occurrence. The rth occurrence is after time t. That means somewhere here we should have rth occurrence after time t. That means in the interval 0 to t, there should be at most r minus 1 occurrences. Okay, so that means tr bigger than t if and only if number of event occurrences in the interval 0 to t less than or equal to r minus 1. That is xt less than or equal to r minus 1. Therefore, the probability of tr bigger than t can be replaced with probability of xt less than or equal to r minus 1. So, this one we can write 1 minus probability of xt less than or equal to r minus 1, and we know the probability distribution of xt. So, we can write this one using the PMF summation k equal to 0 to r minus 1, the probability of xt equal to k. Okay, now we can plug in PMF value, probability of xt equal to k, it's going to be this. Okay, probability of xt equal to k is what? E power minus lambda t to the power of k by k factorial. If you separate the k equal 0 term, okay, so you will write for k equal 0, you will actually get e power minus lambda t here, e power minus lambda t minus summation k equal to 1 to r minus 1 e power minus lambda t to the power of k by k factorial. Okay, this is the CDF value at t for t positive. Okay, so therefore this is the CDF we got for t positive 1 minus e power minus lambda t summation k equal to 1 to r minus 1 e power minus lambda t to the power of k by k factorial for t positive, 0 for t less than or equal to 0. Okay, now let us find out PDF of this capital TR. How do you get the PDF of the capital TR? Simply differentiating CDF of the capital TR. For t less than or equal to 0, CDF anyway 0, derivative also going to be 0. Only for t positive, let's try to differentiate here. Here, I'm trying to differentiate CDF value for t positive. To do this differentiation, let's do term by term differentiation here. So if I take differentiation inside, derivative of 1 going to be 0, and derivative of minus e power minus lambda t is lambda e power minus lambda t. And again, we're trying to do term by term differentiation in the summation. Okay, now again, to perform this differentiation, again let us use UV rule, u v dash plus u dash v, right? So the next step, we can write like this is like a u, this is like a v, u v dash, so e power minus lambda t, derivative of lambda t to the power of k going to be k lambda t to the power of k minus 1 into lambda by chain rule. Okay, and u dash v, derivative of e power minus lambda t going to be e power minus lambda into minus lambda by chain rule and lambda t to the power of k. This is the derivative of e power minus lambda t to the power of k by k factorial with respect to t. Fine. Now, in each term we can see lambda e power minus lambda t, we can take it out. Okay, So if we take lambda e power minus lambda t out, here we have a 1 summation k equal to 1 to r minus 1. Here k by k factorial, we can write k minus 1 factorial. So we have here lambda t to the power of k minus 1 by k minus 1 factorial. Here lambda t to the power of k by k factorial. Okay, this whole thing gets simplified to lambda e power minus lambda t to the power of r minus 1 by r minus 1 factorial. The reason is this. Okay, let me do here lambda e power minus lambda t 1 minus for k equal to 1 the first term here lambda t to the power of 0 by 0 factorial, that will be 1 lambda t by 1 factorial. For k equal to lambda t by 1 factorial minus lambda t whole square by 2 factorial. For k equal to 3, lambda t whole square by 2 factorial, lambda t whole cube by 3 factorial, and so on. The last term going to be lambda t to the power of r minus 2 by r minus 2 factorial minus lambda t to the power of r minus 1 by r minus 1 factorial. As you can see, everything get cancelled except the last term here. So minus into minus, it will be plus. So here we have a lambda e power minus lambda t, and the left over the last term, which is lambda t to the power of r minus 1 by r minus 1 factorial. This is for t positive, and obviously 0 for t less than or equal to 0. So this is going to be our PDF when t positive 0 for t less than or equal to 0. Okay, here this capital TR said to have Erlang distribution with a parameter lambda and r. Lambda is called rate parameter, r is called shape parameter. Okay, so let's go to see next. Here TR is said to have Erlang distribution with a rate parameter lambda and the shape parameter r. Okay, here lambda is any positive real number, but r is positive integer. Okay, it's like a 1, 2, 3 like that, because what is r? Time taken for rth occurrence. R is the positive integer, right? So now this Erlang distribution actually going to be special case of gamma distribution, because we can rewrite the PDF of TR like this. The denominator r minus 1 factorial can be replaced by gamma r, because when r is a positive integer, gamma r is nothing but r minus 1 factorial. So we can rewrite the PDF of TR like this. Okay, so now let me state what is a gamma distribution. A random variable x is said to have gamma distribution with a rate parameter lambda positive and shape parameter alpha positive if its PDF is given by f of x equal to lambda e power minus lambda x to the power of alpha minus 1 by gamma alpha for x positive, 0 for x less than or equal to 0. Here alpha is any positive real number. In Erlang distribution, r should be positive integer. But here in gamma distribution, alpha is any positive real number. That's why Erlang distribution going to be special case of gamma distribution. Okay. Here we have notation for this. We read it as x follows gamma distribution with a parameter alpha comma lambda. And from assignment 3, we know that expectation of x is alpha by lambda, variance of x is alpha by lambda square, and we also looked at MGF. MGF is going to be lambda by lambda minus t power alpha, which makes sense when t between minus lambda to lambda. Okay, these things we know from assignment 3. Okay, here is an exercise. If x follows gamma distribution with a parameter alpha comma lambda, then show that mean mu equal to alpha by lambda, variance sigma square equal to alpha by lambda square through its MGF. You know how to find mean and variance through MGF, right? Please do it. Okay, now let me show you the graph of the PDF of gamma distribution for various values of alpha and lambda. I told you that alpha is a shape parameter, lambda is a rate parameter. Actually, when I change the lambda value, the graph only scales. That means it either stretches or shrinks. But when I change the alpha value, the shape of the graph actually changes. Let's try to see this. The blue curve that you see now is actually for alpha equal to 2, lambda equal to 2. Now let me change the lambda. Let me decrease actually. As you see, the shape of the graph will not change. Only thing is it stretches or shrinks. Now let me change the alpha value. Okay, let me increase. See, as you see, as I keep on increasing alpha, it more and more look like a normal curve, bell-shaped curve. So there is no skewness anymore. It's completely looking like a symmetric. Okay, that's what happens when you change the alpha, which is a shape parameter. That's why we call shape parameter. Fine. Problem: the CPU time requirement capital T for jobs has a gamma distribution with a mean mu equal to 40 seconds and standard deviation sigma equal to 20 seconds. A job taken less than 20 seconds is a shorter job. Okay. What is the probability that of 5 randomly selected jobs, at least 2 are short jobs? Okay. Each of the 5 randomly selected jobs may be shorter or not. If yes, we may call it success or else failure. So observing these 5 randomly selected jobs is like a performing sequence of 5 independent identical binary trials. If we let x denote the number of short jobs in 5 randomly selected jobs, then x follows binomial distribution with a parameter 5 comma. The probability of success we don't know yet. Once we know that p, all we need to compute is probability of x greater than or equal to 2. What is the question here? What is the probability that of 5 randomly selected jobs, at least 2 are short jobs? That means we are interested in probability of x greater than or equal to. So once we figure out this p, we can actually compute using binomial distribution. Okay, fine. Here, capital T, which denote the CPU time requirement for a job, actually follow gamma distribution, but we don't know the parameter alpha and lambda. But we know mean, mu, and standard deviation sigma. From these two, we should be able to figure out alpha and lambda, as we have a connection between mean and variance and these parameters. In fact, we know for a gamma distribution with a parameter alpha lambda, mean mu equal to alpha by lambda, variance sigma square equal to alpha by lambda square. So we are kind of given alpha by lambda, which is the mean 40, and since we are given sigma, sigma square going to be 20 square, which is 400. So alpha by lambda square going to be 20 square. That implies alpha by lambda square is 400. Okay, so we know alpha by lambda 40, alpha by lambda square 400. So if you take 1 by 2, then you will get lambda value 1 by 10. If you take this lambda and plug in 1, then you will get alpha value 4. So we figured out this alpha and lambda. So therefore this t follows gamma distribution with a parameter 4 comma 1 by 10. Here alpha equal to 4, lambda equal to 1 by 10. Now we should be able to write down PDF of t using gamma distribution. Okay. This is actually PDF of the gamma distribution for alpha equal to 4, lambda equal to 1 by 10. Okay, let me rewrite this. 1 by 10 by 3 factorial means 1 by 60 t by 10 whole cube e power minus t by 10 for t positive, 0 for t less than or equal 0. Okay. Now let us try to figure out the probability of success that we talked about. Okay. Let A be the event that randomly selected job is short job. Short job means success, right? Okay, then our probability of success P going to be probability of A. How do you compute probability of A? A happened if time requirement is less than 20 seconds, right? That means the probability of A going to be probability of capital T less than 20. Capital T denote what? Time requirement for job. Okay, if this should be less than 20 seconds, that's then we call shorter job. Okay. Now, to compute probability of t less than 20, we have to integrate the PDF of t from 0 to 20. So, we have to integrate this PDF from 0 to 20. To integrate this, we make a substitution. Let's take y equal to t by 10, then dy equal to dt by 10, then y limits change to 0 to 2. Okay. Then P going to be 1 by 6, 0 to 2 y cube e power minus y dy. Okay. So 1 by 6 times this integral going to be equal to 0.1428765. Okay. Let me show you how do we do it. Let me clear this. Let me take in general in equal to integral 0 to 2 y to the power of n e power minus y dy. Now let me rewrite this one. I want to use integration by parts. 0 to 2 y to the power of n d of minus e power minus y. Now this look like a u dv. I'm going to write now uv, which is a y to the power of n minus e power minus y, 0 to 2 integral 0 to 2 v du. What is v here? Minus e power minus y. The derivative of y to the power of n going to be n y to the power of n minus 1 dy. So next step I can write 2 to the power of n minus e power minus 2 minus 0 minus into minus plus n 0 to 2 y to the power of n minus 1 e power minus y dy. Again, this look like 2 to the power of n minus 2 to the power of n e power minus 2 plus n in minus 1. So in equal to, we got this recurrence relation, in equal to minus 2 to the power of n e power minus 2 plus n in minus 1. We can immediately see I0. When I put n equal 0, simply integral 0 to 2 e power minus 5 dy. This is going to be minus e power minus 5, 0 to 2. It's going to be 1 minus e power minus 2. Okay. That is I0. Now, repeatedly what you do, now I want I3, right? This is actually what? P equal to what? 1 by 6 I3. To get I3, what you do repeatedly, minus 2 cube e power minus 2 plus 3 times I2. Again you have to get I2. I2 is what? Minus 2 square e power minus 2 plus 2 times I1. Again you need to get I1. What is I1? Minus 2 to the power of 1 e power minus 2 plus 1 times I0. I0 we already got. You put it here, you get I1. You put it here, you get I2. Take it I2 and put it here, you get I3. So you put I3 here, you get the P value. That will be 0.1428765. Okay. Feel free to verify this. Okay. Next. So we got P. If x is the number of short jobs out of 5 jobs, then x follows binomial distribution with a parameter 5, 0.1428. Here we are interested in probability of x bigger than or equal to. Because our question is, what is the probability at least 2 of the 5 jobs are short jobs? That means we are interested in probability of x bigger than or equal to. Probability of x bigger than or equal to, we can write 1 minus probability of x less than 2. X less than 2 means x can be 0 or 1. So 1 minus probability of x equal 0 minus probability of x equal 1. Now using binomial PMF, okay, we can actually plug in probability of x equal 0 with this, probability of x equal 1 with this. So all thing gets simplified to 0.1519. Okay, therefore the probability of x bigger than or equal to is 0.1519. Fine. Okay, let me stop now. Thank you.